Hello everyone, my name is Alexander Matrosov and I will be presenting today UEFI Firmware Rootkits, Myths and Realities. So it's a revisited version of the talk specifically for Black Hat Asia, and we have today a lot of cool stuff which is not presented before. So I'm working for Silence, have fun with BIOS and reverse engineering, and I'm former firmware security researcher from Intel. My colleague Eugene Rodionov today is not here. Unfortunately, he can't make it today, came for presenting with me. He is working for Intel Corporation and previously worked as a rootkit researcher for ESET. So this talk already been presented on a few conferences, but specifically for Black Hat Asia, I add some cool stuff. And also today we will be demonstrate the demo of installation of UEFI ransomware on Windows 10 Enterprise version with all updates and also active device guard, virtual secure mode, and secure boot. And it will be cool to see how actually modern UEFI security looks like. And also, we will be cover a lot of topics which is related with firmware implants and rootkits, and also we made some reverse engineering of compute trace. It's not like exactly a rootkit or implant, but the technologies which is used in this legit software very close to implants and rootkits technologies, and they have very similar techniques. Which you can also see in the rootkits usually. In UEFI ransomware, we will be also disclose a timeline and vulnerabilities which actually allow us to install the ransomware from the user mode of operating system to SMM, system management mode, which is most privileged mode on the x86 platforms. Also, we will be briefly discuss forensic approaches for BIOS and some mitigations on the most recent hardware platforms, which is being released like latest few years. So let's start from some history of BIOS rootkits. And actually, it was not a lot of different samples in the wild known. And if you can see, till 2013, we have just few examples of UEFI rootkits in the wild, which is like very old virus Chernobyl sample, which is pretty related with some of tricks which is can used on the old legacy BIOSes by rootkit implants. Compute trace, a lot of researchers already pay attention on compute trace software and did some research in 2009, and actually in 2011 Mabromi showed up, which is actually first known BIOS kit in the wild, and also we can see a lot of different researchers made a research in this field, but after 2013 actually much more attention to the BIOS security, and also we can see how many different vulnerabilities being released, and this kind of issues can be used for rootkits and implants installation. So, and also on public show up some of information about hardware implants for BIOS implants, which is used by some of the agencies for tracking activity on infected laptops. So let's start discussion about UEFI rootkit infections. How actually generic way of infecting BIOS can look like. And here is scheme which is start from operating system user mode exploit, which is raise a privilege escalation to kernel mode, and from kernel mode of operating system you can allow to communicate with the BIOS, and also you can actually send some requests to SMI handlers, which is kind of callback function to operating system level from the BIOS, and you can pass some parameters or buffers. And in the past, it's been known a lot of issues with SMI handlers. And the main thing, if you find some vulnerability and can execute code into the system privilege mode, you can actually make some more interesting things. As example, modify some policies to the BIOS protection bits and try to actually achieve installation to spy flash memory, which can allow attacker to be persistent, and actually nothing will help reinstallation of operating system. And if the malware or implant will be block the updates to the BIOS, it can be stay for the years inside this hardware. And so actually, it's kind of generic scheme, but today our live demo will be show some example of how we can follow this technique to be persistent in spy flash. Also, I want to pay some attention on recent, not some of them it's already known year or so, but this kind of issues can be used for persistent rootkit installation or implant. So actually SMI handlers, it's pretty old techniques for attack the BIOS and already known years, but it's still in the scope and can be very valuable if you think how you can attack the BIOS or find the issues in this scope. And actually, today we also will cover some vulnerabilities into SMI, one of the SMI handler of American Megatrends BIOS framework, which is used by Gigabyte for one of the victim hardware, which we will discuss today. So next vulnerability is S3 boot script, which is very known and being presented in end of 2014 by Rafal, Corey, and Zeno from Legbacor. And they actually found very cool bug, which can use for not only like rootkit installation, but also like disclosure of full physical memory region, and you can actually discover any passwords or sensitive information which is stored into the memory and not encrypted or have a weak encryption algorithms. Think Pawn, the issue which was disclosed by Crash, Dmitry Oleksiuk, last year, and it's actually pretty interesting arbitrary SMM code execution exploit, which is directly can deliver some shellcode for executing into system management mode. And most recent thing is Apteocalypsis, which is show very cool technique of bypassing SMM check. It's kind of prevention and mitigation technique into the BIOS, which can prevent some of the code executions into SMM, but this exploit use first known on the public code reuse attack and actually successfully bypass system SMM checks. Okay, let's discuss what kind of implants and rootkits we have in the wild and which is actually interesting in our opinion. And first known rootkits, which came up on public and related with UEFI firmware, it is Hacking Team Vector EDK. And actually, what is interesting here, it's very simple, but it's also used very powerful techniques. As example, it has an NTFS parser inside inside firmware implant, which is allow vector EDK to change any file inside file system from the BIOS, and actually exactly this way use it to deliver specific agents from hacking team malware. And I will be not describe in the details hacking team, because I already talked about hacking team a lot of times, and you can check my slide deck from 0 nights, because I want to focus on some new stuff today more. But actually, hacking team implant, it's copy of the slide from hacking team leakage and data leak, and you can see actually the proposal to install this implant by physical access with the SPI flash programmer. But actually, if you have exploit from kernel mode in SMI handler, and you can reach that from the kernel mode of operating system, and this firmware exploit can deliver the payload, and if you have some other stage, you can actually do this remotely, and we will show in the demo how we can do that from the docx file for Microsoft Office. Yeah, this screenshot actually show how it's visible into UEFI SPI flash capsule update. You can find by the name RK loader, and it's actually very simple to find inside infected machine. But also, it's just because probably it's being used just for specific target, or just like some synthetic example of or POC, which is not show real implant by hacking team. We don't know, but it's very simple, as I mentioned, and in real case, it's very easy by forensic approaches, which I will discuss today, to find. But we have also some known state-sponsored attacks, like a dirty bouncer, which is being discussed in some document leaked by Edward Snowden. And we don't have exact examples of dirty bouncer, but we try to reconstruct how it can work by the documents, and looks like actually after the attack of the BIOS, it's used the kernel bootloader, actually operating system bootloader patching for like deliver malicious code before operating system loader. But this happens from the BIOS, not like a classical bootkits with the boot sectors like MBR or VBR. But we don't have any confirmation. It's just like based on some theoretical research of the documentation, but probably it should be looks like that. Banana Ballot and JetBlow, which is used by Equation Group and leaked by Shadow Brokers last year, have like more interesting stuff, because they actually share some samples, and these samples use it for in fact the BIOS of Cisco routers, and actually Cisco used some legacy BIOS on these platforms, which is attacked by JetBlow. And we made some reverse engineering on the samples, and if you can see on the black screen, it's actually the XML file with the command of installation, the persistent implant to the BIOS. And on the left side, you can see like some names of the functions, because actually this this BIOS update not clean the names, real names of the functions, and you can see here like the names related with the BIOS. And if we decompile like the function which is deliver the BIOS infection, you can see here like a lot of comments which is point us to the idea how it works. But also, it's like legacy BIOS, not UEFI based, and probably it's working on some old routers. But what is also funny, the debugging symbols not being stripped, and we can see like all the names of source code files here, which is pretty pointing us on the idea what kind of architecture this BIOS implant has. Yeah. But most recent leak is a Vault 7, and it's actually pretty interesting because it's mostly Der Starke. It's like most focused on the MacBooks, not on new ones. Actually, it's like 2 years old, and specifically in the documentation, which is leaked, we also don't have any samples. We have a clue it's being used S3 boot script for like initial infection. And before, like on Zero Nights, we already mentioned in our talk, specifically this vulnerability, it's like very can use for like persistent implant installation. And here's like confirmation, it's already been in the wild and used for some state-sponsored things. How actually it works, and related with documentation, it can hook firmware update process, which is it's actually very interesting because when the firmware update map to specific memory region and call specific SMI handler to deliver the update to SPI flash, before of that, implant patch this BIOS update into the memory and keep the infection in the already updated the BIOS. And when it will be updated the SPI flash, we already have the same malicious contact inside our SPI flash, and it will be persistent. And next update will be probably happen the same if implant have if the BIOS don't change a lot, or implant will be updated remotely from the outdoors, I don't know. So also it's this documentation from Vault 7 leakage about Der Starke components describes some of the UEFI models, and we can see here the loader, which is actually delivers implants from the OS. And as example, if like hacking team mostly discussed like physical access or evil mate attacks, here is we can see confirmation for like remote vectors of installation. I don't want to like focus too much on already known things, and here just like probably most important thing, it's PA part, which is pl.uefi loader, because this driver specifically will be loaded on the PA stage to modify the BIOS protection bits in the platform to open the BIOS for the modification from the operating system level. And actually, if we have any agent component working at the operating system level, it will be allowed to modify the BIOS very easily. And it's actually probably the way how the updates came to this specific implant. With my colleague Eugene Rodionov, we make some also compute trace low jack reverse engineering, and it's actually not implant or malicious software, but as I'm already mentioned, it's pretty close to actually it's used pretty similar techniques which is used by implants, and also it's persistent inside a lot of laptops by default. As example, all the ThinkPads and actually most of the enterprise laptops by default have compute trace already into the BIOS, but it's not active. But who knows if it will be some vulnerability which can activate remotely this software, and it's actually can communicate remotely with some of servers to get updates of the agent. But let's discuss how it works. Yeah, it's actually activated from the BIOS, and here we go. Architecture of compute trace looks like that. So we have for the Dixit drivers inside the BIOS, which is actually installer, update agent, and we have some components which is delivered to operating system, and these components communicate with, let's say, command and control server, which is deliver updates for the agents for the operating system level, not for UEFI. And actually the name of the agent is RPC netp.exe, and if you see this process inside your laptop, it's not hiding itself. If you see this process, probably the compute trace is active on your machine. And if you not activate the compute trace yourself, probably you should think about how it's started. And if you look into installer of a Dixit driver, you can find the names of auto check bug and RPC nettp, and it's actually very interesting. Your operating system, Windows, already has auto check inside Windows folder, and in the installation process, this executable changed, but actually how it works. In the legacy BIOS, it's just use NTFS parser to direct replace this executable into the file system. And on the first part, we discussed hacking team implant, which is also has NTFS parser. And as I mentioned, it's pretty close, use similar techniques. And actually, auto check is not signed for the legacy BIOS. But on the modern UEFI BIOSes, compute trace use specific SCPI table, VBPT, and actually pretty good description and research about that already released by Alex Ionescu, and you can find this link on the end of the slides. And what actually VBBT doing, it's specific SCPI table and started actually from Windows 8 for delivering and recovering some of the software to operating system level. As example, after reinstallation or recover from a specific partition, if you already have pre-installed on Lenovo laptop or some other laptops operating system. So, and actually compute trace used pretty similar thing, and they actually deliver through this SCPI table executable, which is run into the context of SMSS process. And in this case, the binary is digitally signed, which is actually the difference with the legacy. Also, we can see here, it's signed by Symantec and certificate to Absolute Software, which is developers of compute trace. Here is some function which is deliver agent to the file system, and it's the NTFS parser from the Dixit driver. Yeah, here you can see it's find specific file auto check exe, and we also reconstruct the layout of SCPI tables, and specifically into the memory. It looks like that. You have like agent image and 4 specific SCPI tables related with compute trace agent installer. So probably I will go a little bit faster because I have a lot of cool stuff for today. So actually, CompuTrace have some configuration which is related with Lenovo Security Config Dixie driver and also like deliver through UEFI variables in NVRAM. And here is a function which is reconstructed and use it for delivering and reading authenticated variables. And here you can see like some specific callback functions which is not SMI handlers but use it for calling by specific protocol inside the Dixies. But let's switch to some cool thing which is I prepared specifically for Black Hat today. It's UEFI ransomware story. And actually, I just checked it today on the morning, and all the issues which I will be discussed today for the Gigabyte hardware, it's not patched yet. And it's actually very sad because it's more than 90 days we discussed with them some updates, and some of the updates, it's just one bit change inside the BIOS setup configuration, and they not did that. Here is timeline of discovery, the issues which we will discuss today, and we start the discussion in the December of 2016, and actually US CERT being in the loop of all the disclosure process, and we have some acknowledgement from them which is like 507496, and Gigabyte point, it's not their issues, it's American Megatrends issues. And American Megatrends actually mention some of the issues already patched by a new framework, but we asked them to share with us some CVE numbers to just mention in our disclosure process. We have already patched these vulnerabilities, and it's related with this CVE and this issue specifically for Gigabyte hardware. But actually, we don't have any response with CVE numbers for these issues from American Megatrends yet. So, and just like few days ago, Gigabyte responded to us, they will patch these vulnerabilities soon, but we don't know when, and it's still not patched. What kind of hardware we affected? We use actually pretty recent Gigabyte Bricks platform, which is make a proposal from them for enterprise, and they recommend to use in hospitals, government, factory, bank ATMs. And also, today we will show the demo how we can use these issues from Windows 10 Enterprise. All the updates is installed, virtualization-based security is active, and device guard is enabled, and secure boot is also enabled. And the platform, hardware platform actually use pretty recent Skylake CPU, which is Core i7 with vPro. Yeah, so it's actually a very serious proposal being before copied from Gigabyte website. They make a proposal to use this hardware for the hospitals, government, and a lot of sensitive places. But we have following issues, which is actually BIOS lock not enabled. I'm already mentioned like pay driver involved 7 leakage, whereas specifically they load on the very early boot process of the platform specific pay model for deactivate BIOS lock, but here is just not enabled by default. And it allows the attacker to modify BIOS write enabled bit and update the spy flash. Also, firmware update process on the Gigabyte platform don't verify any digital signatures. We just can deliver any BIOS, and it's not signed. SMI flash, SMI handler have multiple vulnerabilities. which is actually not just only classical SMI callouts, it's also like some code execution bugs, and attacker can elevate privilege to system management mode. Yeah, here is like, you can see like BIOS lock is not enabled, and also like SMM BVP bit also stay in 0, and don't any SPI flash regions is protected by PRX registers. So how actually our UEFI ransomware POC works? So we have the doc file, which is embedded into which has some embedded PowerShell dropper, and PowerShell dropper download BIOS updater and deliver through like legit BIOS updater software by gigabyte custom BIOS update to the SPI flash. Then and update is delivering through SINET driver by AMI, and actually this driver maps the update in specific memory region and calls SMI flash handler, and then SMI flash handler flash it to the SPI flash new update. So I think it's good time to demo. We have a gigabyte platform which is start booting. So Windows 10, just log on screen. Oh, sorry guys, I will probably start from the beginning. I don't know why, but it's not visible. Okay. So yeah, we have a gigabyte platform. One moment, something happens wrong. Okay, now we go. So just from the beginning, we have a gigabyte, then it boots Windows 10 Enterprise. Yeah, and I just recorded this demo before my flight on the next day of the conference. So yeah, it's Windows 10. We currently start MS Info 32 to show the secure boot and device guard, and virtualization-based security is enabled. And you can see here, probably it's very difficult, but it is. Secure boot is enabled. And also we enabled BIOS log because currently we update the deliver malicious BIOS through legit update process, and we don't need disabled BIOS log. It can be enabled. Yeah, we start the doc file, run some embedded script. Here is elevate privileges for starting the driver for the update. And now actually the system is freezing because it's called SMI handler, and the SMI handler freezes the system to map and start flashing to the SPI flash. And it's specifically for like if the user by mistake can reboot the platform, it will be damage the BIOS, and then platform will be not booted again. and it's like take 2 minutes to flash the update to the platform. And also, our ransomware POC is started on very, very early boot of operating system. And the first what you can see is the black screen, because we're waiting when output will be available for us for showing the lock screen. Yeah, now the system reboots. Spy flash memory is very slow, why it's take a while for update. And now actually its black screen is appears because we're waiting when the platform will be initialized for make some output. And actually after 30 seconds it will be get opportunity to show the output. Ooh, UEFI ransomware POC specifically for Backathesia, and we guys need all your party invites. Okay, but we think it's not fun just have the lock screen. We modify also the bootloader, and it will be appears soon. It's no more gigabyte on this platform. Yeah. I think it will be appears very soon, and yeah. But we decide to not boot the operating system and just lock again the platform. And that's it. We have a persistent ransomware. Always when the system will be reboots, it will be show this lock screen. And probably convinced user to look Mr. Robot TV show. So yeah, on this platform, BIOS lock being enabled, you can see BLE is set up to 1 and BIOS write is 0. And it's exactly because of we use some vulnerability with not authenticated BIOS update and deliver the update through legit updater. And actually the driver of AMI being signed. And actually this driver can call any of SMI handlers, not just specific SMI flash handler. And it's pretty dangerous because you can just reuse for like persistent installation something bad, not just fun POC which we used for demonstrate. And here is no issues, by the way, from Microsoft. It's just like the issues related with the BIOS. But let's talk actually what happens if the BIOS update is authenticated. We can actually back to code execution with SMI flash Dixie driver, and then it will be allow us to change BIOS lock if it will be enabled and deliver from the SMM malicious update for the BIOS, or modify just like already existing spy flash memory. So yeah, BIOS update process actually, this proposal, it's pretty old. Actually, it's been from 2011 on Intel software forum presented, and AMI already from 2011 have some update process for signed capsule updates, but Gigabyte decide not use that. And just we don't have this part through BIOS updates. but we also have SMI flash handler, which have specific callback functionality for like read, erase, write of SPI flash memory. And here is no checks for validating SMI handlers, which is actually already being proposed by Intel years ago. And SMM is buffer out SMM valid. Check for the buffers is from user space mapped to SMM. And this code actually even exists in open source EDK, but not in Gigabyte BIOS. Okay, and also we have some fun reverse engineering of MS Device Guard Dixie driver from Lenovo laptop. And we find interesting vulnerability description on Lenovo website, which is like have some proposal to bypass device guard from the BIOS through like abusing Dixie driver. And we think, wow, that's cool, actually it's interesting, and decide to look deeper how it works. So on the laptop, it was like P50 Lenovo laptop, pretty recent with Skylake Xeon on board. And it's a screenshot from the BIOS menu when you can see like you can enable device guard Dixie driver into the BIOS. And why it actually exists? When you enable this device guard functionality, you actually lock your boot order, and also you can change secure boot to off mode. And we actually look into Lenovo device guard Dixie driver and find it's communicated with some specific Lenovo security configuration module. And actually, through Lenovo security configuration, it's have access to authenticated UEFI variable in NVRAM. What is mean authenticated? Actually, everybody from operating system level can read this variable, but can't modify. All modifications came through the BIOS functionality, which exists in Lenovo device guard Dixie. And we actually dump information from this UEFI variable, and it stores some bitmap, which is actually configure some policy for device guard. And it's Lenovo security config from T540p, where Dixie driver is not exist, and you can see it's just like have a pretty different options. And here is like from Lenovo P50, where is the bitmap bigger, and also all the writes, reads going only through the Dixie driver. But okay, what will be happens if we run BIOS update with BIOS guard enabled, and it will be like DOS to operating system because of the issue inside the Dixie, where is locked to read and write some of specific variables which is used by operating system level, and BIOS update try to modify that through like normal process, and we just have a blue screen, which is kind of fun. And we actually have some conclusions of this reverse engineering of this issue. It's like very synthetic, can be used for modifying device guard policies, but it can be useful for DOS on the platform. And actually, also, it's important to say on Lenovo website, this issue have acknowledgements being discovered by Microsoft researchers, which is cool. So, and let's talk a little bit about the forensic approaches. And in nowadays, it's a lot of discussion how we can identify good and bad biases. But actually, what I can say, any software which is extracted SPI flash memory and doing some comparison or try to find differences with legit update can't guarantee you don't have any infection in your BIOS, because who knows, probably if SPI flash can be modified when it's like tried to be read from the operating system level by the software. And here is some useful SMM memory forensic things, which is if you're able to dump SMRAM memory region from the platform, you can reconstruct the all layout for active SMI handlers on the platform. And you can see if any of them have some not exist on normal platform, but actually for dumping SMRAM, you should have debug access to the platform or vulnerability, which will be allow you to dump this memory. And it's pretty difficult, but it's most useful way to make the forensics, because you actually have a memory layout for exactly drivers which is running inside the SMM. But how actually is SPI flash dump works, and all the software which is dumping SPI flash through from the operating system level, it's communicating with SPI flash controller and try to read the SPI flash region through some specific SPI registers, but sometimes it's not configured correctly, and some of the software can fail on some of the platforms. And also, as I mentioned, implant inside the BIOS can modify request to the SPI flash controller, and actually the reader will have the fake output from the SPI flash memory. And you probably will see nothing malicious or which is looks as infection. Yeah, here is like flash SPI SMI enable, but here is the scheme where the attacker modifying some of the requests, which is we try just show for HSFC, and you can see like attacker modifies this request to SPI, fake it this request to SPI controller, and then reader just have the fake information. Yeah, so actually what we can do in this case, we can just use some tools to dump in the SPI flash memory directly from the SPI flash chip. And it's actually best way, but on the modern laptops it's difficult to reach the SPI flash chip. So yeah, here's some confusions, but for the servers it's very useful technique to make a forensics. But also the thing is, you need physical access. If we're talking about the data center and with thousands machine, you can't go and dump which physically from each of the servers, and you definitely will be use some software in this case, and here is no guarantee. Other thing, it's Intel virtual platform, which is like called CMix. It's simulator which is can used for some research of BIOS, and you can actually have even like virtual debugging for the platform and dump SMRAM. Other thing, it's MinoBoard Max, which is actually a pretty cool platform. And with open source BIOS, if you already have a dumped Dixie driver, you can try to include inside the BIOS for MinoBoard and run on this platform, and then try to have some debugging console on it, because actually this platform have debugging port, but the debugger for this platform is pretty expensive. It's around $2,000. So it's XDP hardware debuggers. So the blue one, it's cost $2,000, and asset one, it's around $6,000. But also you need a debugging port on the platform to using that. Let's say a few words about mitigations. So actually Intel already introduced a couple of interesting technologies which can be used for guarding BIOS, and one of that is Intel Boot Guard, which is deliver verify boot scheme for secure boot and start the root of trust from very early boot state, which is a reset vector, and also all the code for Intel Boot Guard is executing on separate CPU, and actually it's protected for race condition attacks. Yeah, it's the scheme how it looks like, and you can see like boot guard start very, very early. But also other technology is the BIOS guard. And BIOS guard, it's kind of like hardware assisted authentication for the BIOS recovery attacks, and also it's makes some it's guarding SMI handlers for malicious modifications, and it's allowed to execute only signed Dixie drivers. So yeah, it's a scheme. And also I want to mention VSMT, which is specific SCPI tables, which is actually Windows SMM security mitigation table and pretty recent being delivered to EDK. It's this screenshot being made from the GitHub of EDK too. And actually, I very like it the way how Microsoft start thinking about the BIOS security, because as example, they tried to make some profile of your BIOS and what is technologies is enabled on your hardware for protecting the BIOS, and probably in future they will be enable some of the specific functionality on operating system only if you have secure BIOS. And just a second for advertisement my book. Actually, in few months we will be releasing Rootkits and Bootkits book, which is actually include also the BIOS part, and discussing not only like legacy bootkits and rootkits with the boot sectors, we also focus it on the BIOS forensic and BIOS rootkits. So thank you very much for your attention. If you have any questions, and we have a time. Oh. Yes, please.
So how do you usually deal with hardware vendors and client issues that BIOS? Typically, you end up, you say, oh, here is an issue in your BIOS, and they say, oh, yeah, but I can't fix it because the device comes from American megatrends, and then American trends goes back saying, oh, yeah, but the vendor should have enabled the BIOS protection, so it's like back and forth.
Exactly.
How you as a user or like a company which uses some kind of...
It's actually, yeah, it's very difficult because they always point fingers to each other and say it's not our issues, but as example, BIOS lock is not enabled, and as example, Gigabyte say it's not our issue, but it can be American Megatrends issue because this configuration is specifically configured by the vendor. Other thing, it's a semi-handler flash update. Here is more difficult situation because I might send they patch it, but Gigabyte use the vulnerable one. So we'll see how they will be release the update and how it will be appears. We can make some reverse engineering on it, but it's always difficult because the firmware updates, it's not like delivered to all the platforms in one time. It's very dependent when the system administrator or IT security will be delivered to the users, or the user will be download from the website and installed to the platform. And but it's not frequently happens. And actually, how many just normal user updating the BIOS? Probably never. And old issues, which we discussed on the beginning of presentation, can appear like on the pretty recent platforms, which is like 2 years old or 1 year old, but just users not update the BIOSes. Yeah, and it's pretty big problem. As example, if we're talking about the Apple hardware, they have an ecosystem to deliver updates for the firmware, but because they control the hardware and firmware together on one side. Any other questions?
So do you think like wider adoption of open source BIOS will help?
Problem is, in my opinion, it will be never happens because, so, okay, we have an open source BIOS for some hardware for research, Mino board, whatever, but as example, in some of the BIOSes we have proprietary software as a compute trace and how it can be open sourced. And if we don't have source code, will be partially have the source code, but we can't exclude this from our BIOSes updates or whatever, or compile and just set up the BIOS from on our side to our hardware, it will be no guarantee we don't have some malicious things inside. But yeah, it's actually a very difficult question about the open source BIOS. It's a lot of parts which is probably very difficult to open source, which is related with ME or something which is pretty have closed and not disclosed yet on public. Because some of the things have on very early stages pre-boot initialization stage configured. Yeah, so. And actually, how many users need the open source BIOS? Not too much, probably. And here's no business values for the companies. Myself too, but yeah. Any other questions? Yes, please.
So you mentioned that Windows didn't fix this firmware, right? But you said it's not been fixed. Can you prepare this for the users so they stay safe?
So actually, exactly this bit you can manually change in the BIOS setup, but by default is not enabled. Why is that? It is the issue because normal users will be never like touch this bit.
But can you prepare your own version of this firmware, for example?
Because it's not signed, you can make some reverse engineering of capsule update and change configuration part, but it's undocumented. Yeah, you can, but you need some time for that. Thank you very much for coming for my talk.